Happy Friday. Any big plans for the weekend? What is this? Study. That's life these days, right? Feel that way, like that's all you ever do? Y'all are the best students at Nichols. I know that, right? Have I told you this before? Like, look at the numbers. Y'all are the best ones at Nichols. So keep up the good work and sort of keep in mind what it is that you're leading towards, because all of you sort of have different paths that you're going, and all of them are great. Right? They're all great in their own way. So just keep that in mind. This weekend, my dad's in town. My dad's from Mississippi, and so he's here visiting with us. So we're just going to sort of hang out. I'm preaching on Sunday. I preach occasionally at our church. I think that's about it for our weekend. Pretty quiet. We'll go to, like, we have our Saturday routine, and we'll do that. We go for a bike ride, we go to the grocery store, and then we go to the library. And that's sort of Saturday morning. And then Saturday afternoon, my kids, or we all have sort of this long rest time where we just go to our rooms for about 2 or maybe 3 hours. I have a hammock. I'll go lay out in it under our tree house, and we just sort of hang out Saturday afternoon. And Sunday afternoon too, but Saturday afternoon especially. So if you ever need to rest or relax, come to the Young household. It's very peaceful there. Alrighty, number 2, several of y'all said you have trouble with number 2. Those first 4 problems, man, on the OpenStacks, they're humdingers, aren't they? They're difficult. Listen, you won't have any quadratic and you won't have any systems of 2 equations on the test coming up in a few class periods, whenever that is. But I just want to address this a little bit. I'm just going to set it up for you and get you started in the right direction. You have an object that goes at an angle of 40 degrees, and then I think it goes to a max height of 10 meters. Is that right? And then so we know that y is equal to 10 meters. And that's really all that we know. We know that ax is equal to 0 and ay is equal to negative 10. But mostly that's all that we know. So we can do a couple of things here. We can say that y, and by the way, we're looking for v0. What is v0 equal to? We say that y is equal to v0 y times t plus 1/2 ay t squared. And then we also say that the velocity in the y direction at the top is equal to v0y plus ay times t. And then I like to go through and ask myself, what are the unknowns here? Well, I don't know v0y, I don't know v0y, I don't know t, and I don't know t. And this, by the way, is not t, it's t top. But otherwise, I know everything else. I know ay, I know y, and I know vy at the top of the trajectory. And so I could rewrite these equations, and they would look like this. It would be 10, that's y, equals v0y. I'm going to make a little substitution here. I'm going to say that this is equal to 2 times t top, because the total time is equal to twice the time at the top. So I have 2 times t top minus 5, that's 1/2 of ay, times t 4 t top squared. Erase that. There are a variety of ways to approach this, but this is one way that you can solve this equation. And then you could also say that vy at the top is 0, and that's equal to v0y plus ay, which is negative 10, times t top. And then you would substitute one equation into the other. Savannah? The 4, I plugged in 2t top here for t squared, and 2 squared is equal to 4. All right, you would solve these system of equations because I have 2 unknowns and 2 equations, and I can solve that. There's an easier way, right? Who is that? Devlin, are you here? Yeah, this is the one that you used, that you looked in the book and you found that? Number 2. What was that equation that you used? I didn't use it. What was it? Do you remember? I'm not going to tell you. Look, if you look in the book, what they do is they actually do the substitution for you, and there is a height equation That way you can find the height, and you have the height here, and it's based on v naught, and so it makes this a whole lot easier. So, looking through the book, that sometimes helps. Right, Desmond? Yeah, he did it really easily. So, or you can ask Desmond. That's awesome. Okay? Does that help you a little bit? Yeah, folks? Number 2? All right. Listen, we're having a help section. Can somebody hit the lights back there? All right. You don't like it like this? You like all the lights down? All right, I can do that, I guess. There is a help session today at 12:55, and it's going to be in Beauregard 165. That's sort of like the medium-sized classroom in Beauregard, not the huge one, but the one next down from that. If you're not able to make it, but you want to still come, like you still want to receive that extra credit, shoot me an email, and I'll let you know about some ways that you can do that. Okay, but I will give 3 points per session as we go forward from here. That means we should have 6 or 7 sessions, so around 20 points extra credit. There will be some other opportunities for extra credit, but probably not another 20 points, maybe up to another 10 points or so. All right. Let's try some of these quicker questions. You should be good on some of these. Remember last time we talked about Newton's first and second laws. We'll get to Newton's third law today too. But a book is lying at rest on a table. The book will remain there at rest because which of these is the reason the book remains there at rest? Alright, let's do about 10 or 15 more seconds. 10 more seconds. I'm going to stop at 120. 120. 120. Alright, let's see. What is that? D? There is no net force on the book. That's right. It's not that there's a net force, but the book has too much inertia. If there's a net force, you will have acceleration, no matter how big the object is, no matter how much inertia it has. It's not that there are no forces acting on it. In fact, there are a lot of forces acting on the book. There's the gravitational force. We'll see later that the table is pushing up on the book with a force. There are intermolecular forces, all sorts of forces that are involved. It does move. No, it's stationary. But the answer is there is no net force. And then E is really just a replication of the first one. So D is the right answer here. You have an object moving at constant velocity. What is the net force acting on it? More, equal, or less than its weight? Does it depend on the speed, or is it 0? Remember your Newton's second law. Feel free to ask your neighbors if you like. Just to remind you, our Newton's second law is that F equals ma. That's you. Stop at 1 minute, 10 more seconds. Okay, good. E is right. It's moving at a constant velocity, but it has 0 forces or 0 net force. If it had any net force on it at all, it would be accelerating, and it wouldn't be moving at constant velocity. All right, you put your book on the bus seat next to you. When the bus stops, suddenly the book slides forward off the seat fly. You're on the bus comes to an abrupt stop, and your book slides off onto the floor. Why does it do that? Because a net force acted on it. No net force acted on it. It remained at rest. It just looked like it slid off. Did not move. It seemed to, or gravity stopped working on it. Feel free to ask your neighbors what they put. I encourage you to, in fact. All right, we'll stop in about 10 seconds. $105. Okay, good. B is right. No net force acted on it. That means that the book was moving along, but when the bus stopped, in order for the book to stop, you'd have to have a net force acting on it. So it's like it just continues moving in the direction that it was moving. What is that an application of which law? The first or the second law? It's the first, right? That an object will continue in its state of motion unless a force acts upon it. You kick a smooth, flat stone out on a frozen pond. Slides, slows down, and eventually stops. Include which of these? All right, let's stop at 50 seconds. 50. Okay, good. C is right. A net force acted on it all along. That net force is what caused it to slow down. If it didn't have a net force acting on it, it would just continue on for how long you think? Forever, or until it hit something, right? Hit the edge of the pond. Those last two, by the way, D and E, those are sort of Aristotelian ideas that the stone simply ran out of steam, or more importantly, the Aristotelian idea is that it has this natural tendency to be at rest, and that it will always sort of go towards that state of being at rest. All right, let's do one more. Card on a horizontal frictionless table has been given a push and release. What will happen to the cart? Slowly come to a stop. Accelerate constantly. Increasing acceleration. Constant velocity. Or come to a stop immediately. All right, about 40 of you have the right answer, so it means a dozen or so of you don't. So ask around, ask your neighbors what they put. You're probably going to hit the right answer. All right, we'll stop at 45. 45. All right, D is right. It's going to continue with constant velocity. There are no forces acting on it. There's no friction or any other forces, so it'll just continue without accelerating constantly. So we'll do one more. What do you have to do in order to make it accelerate at a constant rate, this cart? All right, let's stop at 35. 35. Oh, awesome. You have to push the cart continuously. You have to provide this constant force in order to have constant acceleration. Let me ask you another important question. I'm sorry. What is the difference between roast beef and pea soup? Anybody can roast beef. That's a good middle school joke for you. Middle school boys tell jokes like that to one another. Laughter and humor. Alright, we'll come back to this in just a bit. Let's continue where we left off last time. So Newton's second law. Oh, this was a MCAT problem. Well, I don't have it for you in the book. I'm just going to give you the gist of it. 1,000 kilogram rocket. Is acted on by a force of 20,000 newtons. What is its velocity after 8 seconds? You'll continue to see some kinematics problems. I mean, on the next test, you're going to have chapter 3 and 4, so you'll see a lot of kinematics in with the projectile motion. But even with the chapter 4 stuff, you'll see some simpler kinematics, kind of like this, where we're integrating the two. The integrating Newton's laws and our kinematics equations. So here I want to know first, what is the acceleration of this rocket? And then once I know the acceleration, I can figure out its speed after 8 seconds. So in order to find the acceleration, what do I need to do? Well, what do I know in this problem? I'm given a couple things. I'm given this. I'm also given this. It doesn't state this here, but we'll assume that it's initially at rest. I think it did in the original problem. So write down what you know. I always write it down on the side of the page. Write down what it is that you know about this problem. What do those numbers tell you? And, identify them as the variables that they are. All right, so the 1,000 kilograms, that's my mass. My force is equal to 20,000 newtons. And then what else do I know about this? What now? Oh, the time, right? I know time is 8 seconds. And then I also know V naught. What is V naught equal to? 0, because he's at rest initially. And so 2 steps we want to do here. First, I want to find what is the acceleration. And by Newton's second law, which is F equals ma, A then is equal to F over m. Just dividing both sides by m. That's going to be 20,000 divided by 1,000. That's equal to 20 meters per second squared. All right, that's my acceleration. And then if I want to know the speed at a particular time, if I ever want to know the speed at a particular time, I look at this equation. It's a parametric equation, which means it gives the speed as a function of time. V is equal to V naught plus A times T, which is going to be 0 plus 20 times 8, which is 160 meters per second. And then similarly, if I wanted to find the position of this object after that amount of time, I could do a similar thing. What is x equal to? It's just traveling through space. X would equal to V naught t plus 1/2 at squared. 0 plus 1/2 of a is 10 meters per second squared times 8 seconds, which is 640 meters. Okay, so as I said, you'll probably see some kinematics problems. Look back at those old tests. In fact, you should have already printed out some of the old tests and been working through them every day. Like you spent, what, 20 or 30 minutes yesterday working through some of those? Some of y'all are spending a lot more than that because you're trying to get this open stacks out. But be working through those old tests. Just take 3 or 4 questions a day. All right, let's let's do a clicker question. I'm going to sort of help you a little bit on this as we go through, but I want you to just take a moment and write down everything that you know. And our approach on this is going to be to take Newton's second law, which is that the sum of the forces equals mass times acceleration. So on this, I want you to draw all the forces that are acting on this block. I have this block that is hanging inside of an elevator, and I want you to label the forces. How many forces are acting on that block? Are there 1 force, 2 forces, 3 forces, 4? How many are there? There are 2. Right, what are they? The 2 forces that are acting on it. Gravity. The gravitational force is pulling down upon it, and then also there's the rope is pulling up on it. Let's see, have we done weight yet? We have. We talked about weight. Let me show you the gravitational force. We sort of did it from an aside. So I have 2 forces acting on this. 1 force in that direction, and 1 force in that direction. I'm going to call this Ft, and this will be Fw. If ever you need to find the force weight, you say that the force weight is equal to the mass times the acceleration due to gravity, which remember we called that g. That's that positive 10 meters per second squared. And so you can calculate then what is the force weight of this block. It's 10 kilograms, 10 meters per second squared. So it has a weight of 100 newtons per unit. We'll see that in just a bit. So what you want to do is do the vector sum of the forces on this side, the mass and the acceleration, which is given, and then you can solve for the tension in the rope. Be careful with your signs. Notice that the acceleration is either up or down. Notice if it's up or down, and think about what that means for the sign. All right, I'm going to step back. I want you to try to work this out. Do your best on it. All right, doing well so far. More have it right than wrong, so that's good. Feel free to talk with your neighbors about what you do. Your first step is to do the sum of the forces. You only have 2 forces. You just want to write out the vector sum of those forces. One's up, one's down. Think about how do I do the vector sum of those forces, and then write that out in equation form. You know what one of those forces is, then you want to find out what the other force is. Then the next thing that you'll need to consider is the acceleration. And be very careful with your acceleration, because notice here our acceleration is downward. And so ask yourself, what will the sign of that acceleration be? We'll do about 10 or 15 more seconds. You'll certainly have a question like this on the test in a couple of weeks or whenever it is, in 2 days, 3 weeks, I don't know when it is. It's not long from now. All right, let's stop at 350. 350. Guess if you don't know. Look at you. You're awesome. So C is the right answer. The sum of the forces, I say Ft minus Fw. That's my vector sum. I subtracted them because Fw is down and Ft is up. Is equal to my mass times my acceleration. And now I can put in numbers here. Ft is what I want to find. Fw is 10 kilograms times 10 meters per second squared. So it's 100. Forces are in newtons. Ft minus 100 is equal to 10 kilograms, that's my mass, times the acceleration, which is positive or negative 2? Negative 2. And so then I solve this for Ft. It's equal to 100 minus 20, which is equal to 80. So C is the right answer. Notice that if you If you just took the weight, it would be this, but that wouldn't be right. If you got the sign on the acceleration wrong, you would have gotten this, and it would have been 120 newtons, but that's not right. If the elevator was going upward, what would the answer be? If instead of going down at 2 meters per second squared, it was going up at 2 meters per second squared, what would the answer be? Huh? It would be A, right? If it was going up, it would be 120 newtons. Now we got an elevator in a big tall building. Just a second here. Big tall building. You go up and it sort of feels like you're being pulled down, like you're heavier than you are. But if you're going down, you sort of lift up a little bit, like you're feeling lighter than you are. It's the same effect here. Here? Yeah, but I wouldn't do that because it's going to make problems later a little bit more difficult. All right? Like we're trying to build up to a process here, which this is the simplest, but we'll build up to more difficult processes soon. Okay. Let's try this one. And again, I'm going to help you a little bit on this. I want to know what is the tension in the rope on the right. You have a homework problem that's similar to this. Actually, your homework problem is more difficult for this because it has two angles here that are different. The 50 degrees are two different angles. That is your workbook and your problems in the workbook. But here I have a few forces acting on this block. Anytime I come to a problem like this, I want to ask myself, what are all the forces that are acting on this object? And so think about it. I'm going to tell you there are 3 forces. Think about what are the forces that are acting on this block. What are the 3 forces that are acting on this block? What are the 3 forces acting on it? I have the gravitational force down, and then I have what else? I have the 2 ropes. All right, so you can draw those. I have one here and one here. I'm going to call these FT and FT, but only because FTR on the right is equal to FTL. We'll see that that's the case, but oh no, I'll put FTR and FTL. Must be L. And then the third force is the force weight. Okay, so now what you want to do, so we're building up to a process, and you have all the skills that you need to do this process, but it might seem a little funky to you. I'm going to draw a coordinate system that we'll see that coordinate system can change, but in this case the coordinate system is best centered upon that block. I can redraw this over here. I'm going to redraw it with my vectors on it. FW, FTR, FTL, and then I'm going to put in my angles. And you have to be careful with your angles. I always like to measure my angle from the x-axis. Don't you? Like to measure your angle from the x-axis? It's a good practice, just because if you start measuring it from the y-axis, some of the equations that we know, they start getting upended, like the x and y components of vectors. No longer is the x component the cosine, and no longer is the y component the sine. It's okay, you can measure your angle wherever you want, but I recommend that you do it from the x-axis. But in this case, check out our angle. We want to make sure that we know this angle correctly. Is this angle 50 degrees? What do y'all think? All right, let's see. So I have a triangle right here. This angle is 50, so that means this angle is 40. So that means that this angle is 50 degrees. We'll see. Jimmy, do you have a question? No? We'll see when we get to inclined planes, which is sort of what we're leading up to, is that you just have to be careful with your geometry and make sure that you're getting the right angle. Okay? Now, you want to resolve those vectors into their x and y components. Listen, as you're going through this, I recommend really that you do every step. that you draw your vectors on your diagram, you redraw it on a coordinate system, you redraw it with your resolved vectors and their x and y components, and then we'll see what we do next. At least for now, do this each step. This is going to be FTR cosine of 50. Over here we have FTL cosine of 50. And then right here, I have FTR sine of 50. And then right here, I have FTL sine of 50. So all I've done is I've resolved my vectors into all their components, and this one's still the same. This is FW. And now the next thing that we're going to do is apply Newton's second law. And Newton's second law says that the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction is also equal to 0. So Newton's second law is F equals ma, right? That net force is equal to the mass times the acceleration. But it can also be applied to either the x or the y direction. And in fact, that still holds true in the x, the y, and the z directions. All right, so we'll say that FTR cosine 50 minus FTL cosine of 50 equals 0. This doesn't really tell us a whole lot except that FTR equals FTL, which is important. Notice that wouldn't be true if the angles were different. But in this case, because the angles are the same, it is true. And then in the y direction, we get this. We get FTL sine of 50 plus FTR sine of 50 minus FW. That's equal to 0. And then I want to solve for FT. Because I know that FTL and FTR are the same, so we can just call that FT. And solve that for FT. And I'll let y'all finish that off. So solve that now for FT, recognizing that FTL and FTR are exactly the same. It's a minus FW. Yeah, because our FW is down. You're doing pretty well so far. The ones that have answered are doing well. About 6 of you don't have it right. This will be one of the more difficult problems on the test. So we'll get into inclined planes, and you'll have several of those. But knowing how to do this will help you with the inclined plane. Following this process, solve this for FT. Ask your neighbor what they put, okay? About half of you have it wrong right now. So ask your neighbor what they put. Do y'all know one another? Can you share your answers with one another? Can you tell her what you put there? Juliana, do you and Savannah know one another? Can you tell your answers to one another, or have you already? You don't know what you asked. Alright, we're going to have more practice. This is one of the more difficult questions. Make sure that you're sharing your answer with your neighbors, okay? Let's stop at 9:05. 9:05. Just guess if you're not sure. Yeah, doing all right. 9:05. Okay, A is right. So from this point, I was just a couple steps left. I would have 2 FT, because FTL and FTR are the same. Sine of 50 equals FW. So FT is equal to FW over 2 sine of 50. And so FT, what was FW? Was 230 newtons. That's 23 times G over 2 sine 50. And that's equal to, what do we say it was? A, 150 newtons. Let me lay out the process that we just went through, and then we'll apply that process every time. The first thing that we do is we draw a picture. In fact, in this one, the picture was already drawn for us, but we draw a picture, and that includes labeling all the vectors, all the forces. Ask yourself, what are all the forces that are acting on this object? The next thing that we do is that we draw what we call a free body diagram. And as you get better and better at this, you'll find that you'll be able to skip some steps. Like maybe you can combine these steps. But the free body diagram, that's this thing over here. This is our free body diagram. That's where we draw our coordinate system. We draw all of our vectors on it, and then we label the angles. You got to be pretty good at your geometry, right? At least your right angle, figuring out your right angle geometry, and be able to get your angles correct and label all your vectors correctly. The next step that we do is we resolve our vectors. Into their x and y components. The next thing that you do is you apply Newton's second law. And so where we resolve the vectors, that's right here. And then this is where we apply Newton's second law. When you apply Newton's second law, you'll get 2 equations. Actually, we'll see with the inclined plane that we might get more than that because we'll have friction and stuff thrown in there. But here we'll get 2 equations. Okay? This is my wife. The loudest sneeze of anybody you've ever heard. I mean, it's gotten better over the years, but she used to, like when we first got married some 15 years ago or whatever, we'd be in the car and she would sneeze, and I wouldn't say anything because we were just married, but it was just like, the loudest thing. It hurt my ears. And then finally one day, many years later, I said, you sneeze kind of loud. And she was, it sort of made her self-conscious. Like, she's not a vindictive person at all. Like, she wasn't mad or anything, but it just made her self-conscious. Then I felt bad because later I learned that she was stifling her sneezes because of me. And she said that she didn't like stifling her sneezes. Like, she was really wanting to let that thing out. So, it's okay to let out your sneeze, is what I'm saying. All right? Okay, so we apply the second law, and then we get 2 equations. All right, why do we get 2 equations? Because we have 2 axes. We have the x and the y. That's right. So I do the sum of the forces in the x, and I do the sum of the forces in the y. We'll see later that we might get more than 2 equations, but at least we get 2 equations. And then number 5, you solve those equations for your unknown. And that'll be different every time. Although we'll see that there are some basic problems that you'll see on the exam, and I'll lay those out for you. But you're definitely going to see an inclined plane. You'll likely see the elevator going up or down, accelerating. But we follow the same steps each time. Okay? Let's do some more practice. Oh, let's look at the unit for force. We've already introduced this. Let me just write it down on paper. The SI unit for force is the Newton. We capitalize it. By the way, units, that's a little bit of grammar for you. When you have a unit that's named after a person, like Isaac Newton, they named the unit after him, then you capitalize the abbreviation, but you don't capitalize it when you write it out. So like, I don't know, what's a unit you'll use in biology? Do units? Math and biology? You'll do math and biology. Anyway, if you have a unit that's named after a person, you capitalize the abbreviation. If you remember, F equals ma, so if 1 Newton is our force, we can look at what are the basic SI units of that. And M is in kilograms, and A is in meters per second squared. As we move up into these, as we sort of build the course on each chapter, we'll begin to encounter units that are not basic SI units. Like up till now, all we've seen were meters, kilograms, and seconds. But now we're going to begin to see new units. And so occasionally on the test, I'll ask you questions. What are the basic SI units for the Newton, for example? And don't memorize that. Just remember what the equation is. F equals ma. And then you can put in the units for M and the units for A. And you can figure out what are the basic SI units, kilogram meters per second squared. You'll see some questions like that on the old test as you go through them, where I'll ask you that. Hopefully that's a gimme question. I hope that everybody gets it right. That's what you do. You just put in the units for each variable. In the U.S., the unit for the force is the pound. And a Newton is about so just sort of to give you an idea of what newtons are. A typical person weighs about 700 newtons. I think that's about 160 or 70 pounds. And a small apple is about 1 newton. 1 newton is about a quarter pound. So I always tell my students that you should go into McDonald's, and what do y'all get at McDonald's sometimes? A quarter pounder burger, right? A quarter pounder. But instead you go in and tell them that you want a Newton burger, and see what they say. I see what the people. Huh? And then you explain to them, no, a Newton is just a quarter pound. I want a quarter pounder, not a Newton burger. It's the same thing. And this is just sort of an interest. Do y'all know what the British unit for mass is? In the metric system, kilogram is mass and Newton is weight. Those are two different things. In the British system, pound is weight. So what is mass? There are actually some different units for it, but the British unit for mass is called a slug. All right, let's try these little quick tests. These are just some old test questions I pulled. True or false? Is this statement true or false? It is possible to have motion without a force. It is possible to have motion without a force. Y'all are split. Like you're split almost evenly on this. It is possible that is, an object moving through space can be moving without a force acting upon it. Ask your neighbor what they put. You're still split. All right, we're going to stop at 58. Okay, the answer is true. It is a true statement that you can have an object moving, but it have no forces acting upon it. Let's try this next one. This next one I don't like, but we're going to try it anyway. It's just a little bit confusing. If an object isn't moving, no force acts upon it. That is, if an object is stationary, there have to be no forces acting upon it. Is that a true statement or is that a false statement? All right, let's stop at 55. Look at y'all. That's awesome. Is that right? False. Yeah, so if an object is stationary, it can have forces acting on it, right? The problem with the block and all the ropes and stuff, there are lots of forces acting on that, but it was stationary, so the answer is false. What do you call Santa's little helpers? Subordinate clauses. What's that? Now I like it. I wanted to be an English major in college. Real bad. But I didn't. You too? It's not too late for you. Alright. Let's look at Newton's... Actually, no, let's do a few more clicker questions. We might just wrap up with this. A very large truck sits on a frozen lake. Assume there's no friction between the tires and the ice, and a fly suddenly smashes against the front window. What happens to the truck? Just to clarify, I want to know what happens to the truck after the fly hits, right? Like after the occurrence of the smashing into the window, in the moments after that. All right, we'll stop at 110 or 112. Okay, good. V is right. It's going to move backward at constant speed. Some of y'all put C, and that's sort of correct too. C is sort of correct, that when the fly hits the windshield of the truck does accelerate backwards for just a moment, but then it continues at a constant speed. Inertia doesn't stop an object from accelerating. It only makes it accelerate at a lower rate. From rest, we step on the gas of our Ferrari for 4 seconds, and we speed it up to a final speed v. What if your force was only half f? How long would you have to apply to reach the same final speed? You have your force, what happens to the motion of the car? And then how does that affect the time required to reach that same final speed? It was 4 seconds. Is it now going to be a quarter that, half that, same as that, twice that, or 4 times that time? All right, let's stop at 110. 110. It's a good question. I like these kinds of questions for the test. They're relationship questions. Hey, look at y'all. Y'all do well. That's good. Hey, what do you call cheese that doesn't belong to you? No. Nacho cheese. It's nacho cheese. All right, so F equals ma, right? If I have half F, I have half the acceleration. If I have half the force, I have half the acceleration. And I also know that V is equal to A times T. So if I have half the acceleration, that means I need twice the time. And so where it was 4 seconds, I now need 8 seconds in order to accelerate to that same speed. This was very similar. All right, let's stop at 55. 55. Very good. C is right. F equals ma. If I have twice the mass, but the same force, I have to have half the acceleration. If I double my mass, given the same force, I'm going to have half the acceleration. And so after the same time, because I have half the acceleration, v is equal to at, I'm going to have half the velocity. So D is the right answer. So you do a couple more. I'll let y'all go. Oh, this one's tricky. All right. Force acts on M1, given acceleration A1. Then it acts on M2, given acceleration twice what it had up here. If that same force acts on both the blocks together, what's the acceleration going to be? Think about how your masses are increasing in each, or how they're changing in each scenario, and what that does to the acceleration. Here I have a mass, an acceleration A. Here I have a mass. What is the relationship of M2 to M1? Is it bigger or smaller mass? Smaller mass. By what factor is it smaller? By factor of a half, right? It's half the mass of M1. So now what happens when I apply that same force to these masses? Mass M1 and a mass that's half that of M1. $22 of you have the right answer right now. So good job. It's 22. Think about your masses and what's happening to your masses. How they're increasing. Let me give you a little hint. This is the way I like to think about it. Get rid of the M1, M2. I just call this M. I'll call this 1/2 M. And then what would I call this? Add 1 M and 1/2 M, then this is going to be 3/2 M, right? Because 1 and a half, that's 3/2. So now, what is my acceleration going to be? Well, I get A here, I get 2A here. So what acceleration am I going to have here? All right, let's stop in 5 seconds at 2:12. Okay, E is the right answer. Because I have F equal ma. I have 3/2 the mass, but I still have the same force, so I have to have 2/3 the acceleration. Because notice how these two cancel one another out. They have to because I still have the same force. We'll see some more of these next time, okay? I understand that a lot of you are a little bit lost right now, and that's okay. But we'll catch up. Help session today, and we'll probably spend a lot of time on projectile motion, but if we have time at the end, we might get a little bit into Newton's second law, so you get a more of a preview of next week. 12:55 in an hour.